Hi, this is Thomas. Welcome to Calculus. We're going today to see how to use the fundamental theorem of calculus to evaluate definite integrals. Before looking at the theorem, we have two requirements. One is that the function of x is continuous for a particular interval on the x-axis. So our interval is a to b. A is less than or equal to x, which is less than or equal to b. So for this interval on the x-axis, the function f of x is continuous, and big letter F of x is the antiderivative of f of x. And with these two conditions, we can state the fundamental theorem of calculus, which is that the integral from a to b for f of x with respect to x is the difference between the antiderivative at b and the antiderivative at a. And we can use this theorem to calculate the area under a curve in this interval on the x-axis. Not an estimate, but the exact value of the area under the curve. Note that in contrast to integrals we've seen previously, which were indefinite integrals, we're now dealing with definite integrals. And definite integrals, or the reference to definite, is the indication that we're evaluating an integral for a particular interval on the x-axis from a to b. So let's look at some examples. First, the integral from 1 to 3 of x squared plus 2 with respect to x. So first I want to calculate the antiderivative for x squared plus 2. And I'll use my antiderivative rules to arrive at x cubed over 3 plus 2x. Now I'm calculating the antiderivative, so I'm not going to attach the constant of integration. I simply want this expression, and I want to evaluate this expression at two particular points, 1 and 3. And I'll subtract the value at 3 minus the value at 1, and that will be the area under the curve on the interval of x equals 1 to x equals 3 for this particular function. So when I input the 3 value into my antiderivative, I have 3 to the power of 3 over 3 plus 2 times 3, which is 9 plus 6, which is 15. And when I input the 1 value, I have 1 to the power of 3 over 3 plus 2 times 1, which equals 1 over 3 plus 2, or 7 over 3. And I'll subtract 15 minus 7 over 3 to arrive at 38 over 3 units squared. That's the area under the curve x squared plus 2 from 1 to 3 on the x-axis. So to have a visual, let's create a graph with our function y equals x squared plus 2 and show this region from 1 to 3 on the x-axis. So I'm going to mark off 2 on the y-axis, and x squared plus 2 is about like this. And if I mark off 1 and 3 on the x-axis and connect from the x-axis to the curve, then the area that I've calculated is bordered by the x-axis, and x equals 1, and x equals 3, and y equals x squared plus 2. In other words, the shaded region is the region we've calculated the area of as 38 over 3 units squared. Let's look at another example. The integral from 0 to pi over 3 for sine of x with respect to x. First, we'll take the antiderivative of sine of x, which is negative cosine x, and we'll evaluate negative cosine x on the interval 0 to pi over 3. At pi over 3, cosine is 1/2, so negative cosine at pi over 3 equals negative 1/2. Subtracting negative cosine at 0, cosine at 0 is 1, negative cosine is negative 1, so this is minus negative 1. Negative 1/2 minus negative 1, or negative 1/2 plus 1, equals 1/2 units squared. Let's draw a graph. For sine of x from 0 to pi, halfway between is pi over 2, and then a little farther to the left is pi over 3. And if I extend from pi over 3 on the x-axis up to the curve, and I shade in the area from the y-axis over to pi over 3, this is the area that we've calculated as 1/2 units squared, bordered by the x-axis, x equals pi over 3, and the curve y equals sine of x. So we've seen two examples of applying the fundamental theorem of calculus to using definite integrals to calculate the exact area under a curve on a specific interval on the x-axis. Be sure to practice calculating definite integrals with examples from your textbook, and thanks for watching.